Today we'll be talking about looking at the liquid-vapor interface of both hexane in water and hydrogen sulfide in water. So why are we interested in such systems? Well, first of all, if we look at liquid-vapor interfaces of water-oil mixtures, that is extremely useful to understand the hydrophobic effect. We can also use that for the petrochemical industry, for enhanced oil recovery, for hydraulic fracking, for mitigation of oil spills, and also to obtain insight into seawater aerosol formation. Okay, so how did we come about this particular, today the study that I'll be presenting to you? Well, a group, I think it was the Max Planck Institute, Musek et al., accidentally came across an interesting result, at least to them it was interesting. And that is, when they were running a water droplet experiment, they left a little bit of hexane and squalene mixture at the bottom of the cuvette, and they saw that the surface tension of water decreased. And that was interesting to them. Why would the vapor of hexane interact with basically the water droplet? And so there's actually, what they then did is they expanded upon their experiment. They looked at different mixtures of different amounts of hexane and squalene, and they saw how the surface tension changed. And at the bottom, I believe you guys can see a quote, right? And this quote basically states that they want more insight into this, and that's exactly what we're trying to do today. So we do that by running simulations. So in order to emulate that setup that I just presented to you, we are running Monte Carlo simulations using the Gibbs Ensemble setup, and that entails having a two-box system in which one of our boxes is a hexane reservoir. So basically a box full of hexane vapor. The other box is our water slab, and that you can see all the way on the left. You guys can see the water with an empty area for the vapor to then swap into. And then we allow only the hexanes to swap between the hexane reservoir and the water slab. And we then observe, where are these hexanes swapping? Are they preferring to be in the vapor phase, or are they actually interacting with the surface of the water? And so we ran them. We got some equilibration steps running, and we also then ran production, and we spawned. We actually had 64 independent simulations running to get really good statistics. So to set this up, as Ilya presented earlier, we have specific force fields that we use. And the force fields that we decided to use for this particular simulation was the TraPPE force field that is developed by our group. It's a 6-site model for the hexane. And we use a TIP4P 2005 water model, which is a 4-site model for the water. The reason why we decided to use that is, if you guys can see, there's here we have some actual simulation data results showing a different simulation run by a different group member, Janine, and we see that getting the interfacial tension between dodecaine and water got almost on point experimental results. So with that, and to make our simulations a little bit more accurate, we also took into account the Hydrophobie-Hydration model that Ashbal et al. Developed, which basically means, so looking at our TraPPE model and our water model, they're both non-polarizable, and so our hexane doesn't actually have charges, and so in order to account for the cross interaction to be more accurate, we basically change our epsilons and sigmas to match up with Ashbel's et al. So that we can have our well depth be closer to what the cross interaction term should be. Does that make sense? Yeah. Okay, so we did that, and we obtained our results. So here we have the surface tension of water, and what happens when we ran at different, basically partial pressures of hexane. So in order for us to actually emulate what the experimentalists did with different concentrations of hexane, we ran at different partial pressures of hexane. Does that make sense? So we had hexane at 95% partial pressure, 75% partial pressure, 50%, and 25%. Now, we ran these simulations, and what do we observe? So with the raw data, we immediately see that compared to the neat water surface tension, we definitely start to see a decrease in the surface tension as our partial pressure increases. Clear?
Yeah.
When we normalize, we see that we actually have a very similar trend to that obtained by the experimentalists presented before. So there you go. So then, we also wanted to understand this a little bit more. So here, we wanted to look at how is the surface density changing as partial pressure increases. So we look at what are the number of, how many hexanes are swapping, where are they swapping, and how many are swapping onto the interface of water specifically. And here we see, again, a change of density and the number of hexanes per, on the surface of our water. And again, we see an increase. So then, to truly determine what our surface of water is, we actually had to take all of our frames and we ran a tan fitting function so that we can actually determine a specific location for the interface of water. And that's what we did. And we also present to you the number of hexanes that are swapping and where they are swapping. So you guys see a peak, right? For the number of hexanes. So this is a Z density profile. So that means, just imagine the water slab on its side, and that is our Z dimension. We were able to obtain the density as a function of Z. And what do we observe? There's a peak of N hexanes around 2 angstroms right above the interface of water, or the surface of water. So that's interesting. So that's where most of the N hexanes are loading, not in the vapor, not in the bulk. Now, and also we observe on the right-hand side, we have a plot there that shows you what are the density of N hexanes as your partial pressure increases. So then we decided to look at how are these hexanes orienting with the surface of the water. So we looked at the order parameter of hexane, which means we took beads 1 and 3. We obtained the vectors between 1 and 3, and we saw how does that vector correlate to the surface of the water. If it is parallel, it has an order parameter of close to -0.5. And if it is perpendicular, it will have a value close to 1. And so you guys see on the, I believe, the left-hand side, right-hand side, I think, of the slide, you guys see the plot, correct?
Yes.
And so what do we observe? Yeah, and there is a slight preferential orientation to parallel. So our hexanes are not just loading perpendicularly onto the surface, they're loading more with a parallel orientation. Okay. Now, we also wanted to look and obtain the partition function. And so the way we do that is we take the vapor density and we divide our Z density profile that you guys saw by our vapor density. And if we had run these simulations and they ran long enough, our statistics should show us that in our vapor area of our water slab, we should have the same density there that we have in our reservoir. And so when we do that, when we divide by the vapor density, so by the vapor density of the reservoir, we should have a value of 1. Does that make sense in the vapor? So what do we see? A peak, right? Right near the interface. And so from that, we are now able to obtain the delta G, the free energy of transfer, basically. And what we observe is that hexanes, yes, we are taught like the hydrophobic effect, it doesn't want to interact with water, but that is a simplistic, interpretation of the hydrophobic effect. What we are observing is that at the interface of water, there is a strong favorable interaction between hexane and water. And also we see that because there's a peak that we look at our KZ plot, which is our partition function, there is an increased favorable interactions between our hexanes near the interface of water. And as we go into the bulk, what do we expect? A very high energy, basically what would be a kind of an energy barrier. Like the free energy of transfer is very high, which makes sense because that is what we're taught. It's a hydrophobic effect. It does not want to fully swap into the bulk, but for the interface, there's a lot of favorable interactions there, while when we go out into the vapor phase, it's close to 0. So it's a little bit neutral. Does that make sense?
Yes.
Yeah. So with that, we actually then want to present to you guys, we started looking at what happens when we have hydrogen sulfide and its interactions with the surface of water. And so in order to do that, we used a force field developed by one of my group members that is implemented in the TraPPE, and that is a four-site model for H2S with a three-site LJ interaction. And the sigmas and epsilons are presented to you there. And immediately, we ran this at 1% partial pressure. So just keep that in mind. For hexane, we had 95, 75, 50, and 25%. But for H2S, initially, we're just looking at 1%. And just at 1%, we see the surface tension decrease from around 69 millinewtons per meter for neat water to 60 millinewtons per meter for the 1% H2S. These are preliminary data. So then we looked and we ran similar types of analysis. So here I believe we have the density profile, right? You guys see that? And we observe that we have a peak of H2S, of hydrogen sulfide, also near the interface of water in this particular case also. And we look at the order parameter, and what do we observe for the order parameter? It's close to zero. There really isn't a favorable favorable orientation there. So H2S is not exhibiting as strong of a parallel orientation as N-hexane. Clear?
Yeah.
Okay. So we did this, and we also looked at comparing it to 25% N-hexane. So 25% partial pressure of N-hexane. And what do we observe? The first thing is that where hydrogen sulfide is loading is closer to the interface than hexane was loading. So it's a little bit to the left. And for So for comparing 1% H2S versus 25%, there's more loading of H2S observed. I believe here we present the KZ and the GZ, correct?
Yeah.
And so for the free energy of transfer, we also observe that H2S is not as unfavorable in the bulk region. It actually shows some favorability compared to the vapor phase. So for H2S, we see that it's more favorable at the interface of 25% on hexane and at the bulk. So H2S has no problem swapping into the bulk compared to hexane. So we can compare that, and we can see how they both are interacting with the surface of water. So with that, I just want to conclude. So from these simulations, first we were able to observe that the surface tension of water decreases as the partial pressure of the system increases for an hexane. And additionally, for H2S at 1%, we see a 15% decrease in the surface tension, just at 1% of H2S. And looking at the KZ plot for hexane, we observe that there is an increased enrichment of that hexane as partial pressure increases. So the hexanes are favorably interacting with each other on the surface of the water. And the free energy of transfer of H2S at 1% is it's more favorable than the free energy of transfer of hexane at 25%. So with that, I hope you guys obtained some insight. I hope that gives you some food for thought about looking at the hydrophobic effect, looking at how hexane interacts with the surface of water and H2S also. So I'd be open for some questions. So I want to thank my advisors, my group, and the DRC and Access Assistance, and Connor Venteicher, and everyone else in this picture and all of my funding agencies. Thank you for listening.
Okay.
I have a question. From the simulation, can you tell whether the hexane would form islands on the water surface because of hexane-hexane attractive interactions, or would it sort of spread out more?
I was not able to determine that, but I can look into it. I mean, what happens is the area that I'm working with is 30, it's a periodic boundary, but I'm only looking at 30 by 30 angstroms squared.
I can answer no, because
we have looked at hexane on gold surfaces and graphene, and the critical temperature is way suppressed because you have interactions only in one direction. So 300 Kelvin is way above the critical point. Of
So no meaning no islands.
no islands. It's very far above the two-dimensional critical temperature of hexane.
Very nice talk. I'm more interested in the opposite. Water is very poorly soluble in hexane. So I was wondering, does that the same observations could be made if you're focusing on the water interaction with hexane? So the surface interface between water and hexane, could you see increase of concentration of water molecules into the initial layer of hexane, and then, I mean, basically the same but in reverse?
So you want to look at liquid hexane with vapor water?
No, so liquid water with liquid hexane.
So looking at the interface of such, like we have some simulations that I've presented, that some of my group members have looked at the interfacial tension between, like for example, dodecane and water.
Okay.
But
So
I think the interesting case would be if we go for an alkane which has a lower vapor pressure than water. So I think if you do hexane, to have a stable system, you have to be at very low pressure. So that means the vapor pressure of water will be very low, and you have overall the water density would be extremely low. So if we go to something like octadecane or a longer oil, that would be interesting, because then we can be at the temperature where we have reasonably high water vapor pressure. And I would expect absorption of water.
Mostly there.
Yeah,
As opposed to going through both.
yeah.
One more question?
So would you expect methane to have the same effect as hexane? Just out of curiosity.
Exponentially smaller because the cohesive energy between methane and water is smaller.
And then the second question would be, if you change the water to salt water, and maybe some people still aren't going with this, what do you think the effect might be?
If we change the water to salt water, I think we would probably see something similar, but I'm not really sure, to be honest.